everyone, and welcome back to Newton's Academy past paper review for grade 12. Today we will be breaking down a physics past paper question, and that will be on the topic of the photoelectric effect. So let's get right into it. Question 11. Question 11 gives us the apparatus shown in the diagram, which is used to demonstrate the photoelectric effect. So we have our apparatus, the incident light, the emitter electrode, the collector electrode, and we have a potential difference or a voltage as well as an ammeter. So 11.1.1 asks, define in words the photoelectric effect. Now the definition for the photoelectric effect is simply the emission of electrons from the surface of a metal which is exposed to radiation. So to explain that, whenever the surface of a metal is exposed to electromagnetic radiation, which is usually light, the electrons in that metal will be emitted from the surface of that metal. Okay, the next part of information tells us that the incident monochromatic light transfers 1.8 times 10 to the negative 9 joules of energy in 1 second to a certain area of the emitter. The wavelength of the photon in the incident light is 260 nanometers. If one photon releases one electron, calculate 11.1.2 the number of electrons released from the surface of that area in the emitter in 1 second. So basically, they're telling us to find out, they give us the total energy that the light wave transfers, and now they're giving us the energy of one photon. So given that we have the energy of this one photon, we need to determine how many photons are in this total energy or in this beam of light, and that will determine how many electrons are released. So we have our total energy, 11.1.2. We have our total energy, and that's the energy of the beam. So energy total is equal to 1.8 times 10 to the negative 9 joules. That's the total energy of the beam. And now we need to find or calculate the energy of one photon. And we can do that using the wavelength that they gave us, because we have a formula for energy in terms of wavelength. So we can substitute into there. H is Planck's constant, 6.63 times 10 to the negative 34 multiplied by the speed of light divided by the wavelength, which was 260 nanometers. And you'll get the final energy value for one photon to be 7.65 times 10 to the negative 19 joules. Okay, so now to determine how many electrons were emitted, we need to simply determine how many photons were in the original beam. Why? Because they told us that one photon emits one electron. So we simply take number of electrons will be equal to the total energy over the energy of one photon, which means we will substitute 1.8 times 10 to the negative 9 in the numerator and 7.65 times 10 to the negative 19 in the denominator, and we will get the number of electrons transferred in 1 second to be 2.35 times 10 to the power 9 electrons. Okay. Looking at our next question, 11.1.3 asks, calculate the current produced in amperes. So current, we know, is defined as the rate of flow of charge. So we know 11.1.3, we know that current is the rate of flow of charge. Now we have the time, but we do not have the charge. So we need to find a way to calculate the charge. And we can do that based on the fact that we have calculated the number of electrons. So we have our number of electrons, which is 2.35 times 10 to the power 9, and we have the elementary electron charge, which is 1.6 times 10 to the power negative 19, and we will get the total charge transferred then to be 3.76 times 10 to the negative 10 coulombs. So we can go and we can now substitute this in our charge value in order to calculate our current. So we say 3.76 times 10 to the negative 10 divided by 1 second, and obviously our answer will remain the same. It's just our units that will change slightly. So 3.76 times 10 to the negative 10, and this time it will be amps because they wanted the current in amperes. Okay, going back to our question, 11.2 asks, the sketch below shows an example of a line emission spectrum. So notice how there are large dark patches with these tiny white or light patches which resemble the frequency of light bands emitted. 11.2.1 briefly explain how this type of spectrum is formed by referring to the electron transition in atoms. So this is quite simple. 11.2.1. So the line emission spectrum is formed when electrons are excited into a higher energy orbital. So the electrons are in the excited state. They are in the excited state, meaning they have additional energy, and then they fall back to the ground state. And when they fall back to the ground state, which is the original energy level in which they were found, they emit energy as light, and that corresponds to a certain frequency and wavelength. Okay. 11.2.2 that asks for one important use of line emission spectra. So there are multiple uses. Obviously, you only need to state one. So the primary use would be to identify elements from the periodic table, and then other uses would be in fluorescent lights or in neon signs, or scientists sometimes use them to determine the temperature of stars. But the main use here is to identify elements of the periodic table. Okay, and that brings us to the end of this brief question on the photoelectric effect. Thank you for watching.